It is September 2025, and we have finally reached the point where a developer can run an agentic coding model on their desktop computer, or at least, that's what I'm hoping to do. From a hardware perspective, we now have enough compute power and memory bandwidth in consumer-level computers. On the software side, high-quality open-weight large language models perform well enough for coding tasks and can run on the aforementioned hardware. But why go through all this trouble when cloud exists? The answer is sovereignty. Cloud providers control everything: pricing, availability, model behavior, and terms of service. They can throttle your requests, deprecate models, or decide your use case violates their rules. You're renting access to intelligence under someone else's terms with zero control over the underlying system. Local models flip this entirely. You own the weights, control the inference parameters, and decide what constitutes acceptable behavior. Want to fine-tune on your codebase? Go ahead. Need to process proprietary code without sending it over the internet? No problem. Your machine, your rules, predictable performance. On this channel, I'm going to document my journey to achieve what was once a dream: having an artificial pair programmer to work on my ideas with me, tirelessly, under my complete control. Before we dive into hardware specifications, I need to clarify what I mean by good enough, because an AI coding assistant doesn't need to be perfect to cross the threshold of genuine usefulness. When I say we've finally reached the point, I'm not claiming we can run Claude 4 equivalents on our desks. What I am claiming is that we can now run models capable of handling the bulk of day-to-day coding assistance tasks that actually matter. Here's what I'm expecting from the minimum viable coding companion: code review and quality improvements within reasonable scope, identifying obvious bugs, suggesting cleaner implementations. Think of it as a junior developer who's read every coding best practices guide, but lacks deep system knowledge. Spotting edge cases in the functions and modules you're actively working on. It won't catch complex distributed system edge cases, but it'll flag the obvious gotchas that slip through during focused development. Writing comprehensive tests when you're feeling lazy, generating unit tests with good coverage, creating mock objects for dependencies, writing property-based test cases, and handling common test scenarios you know you should write but find tedious. Bridging knowledge gaps for unfamiliar APIs, libraries, or patterns. Refactoring assistance and code cleanup. Extracting repeated code into functions, applying consistent naming conventions, restructuring classes for better separation of concerns. Explaining complex code sections you didn't write. Breaking down dense algorithms, clarifying obscure business logic, documenting undocumented functions, and explaining why previous developers made specific architectural choices. What I'm explicitly not expecting from local coding assistant for now: architecting entire applications from scratch, complex multi-file debugging across large code bases, deep domain expertise in specialized fields like graphics programming or embedded systems, replacing your core problem-solving and design skills. The key insight here is that most coding work involves incremental improvements, small feature additions, and maintenance tasks rather than groundbreaking algorithmic breakthroughs. A model that can competently handle these routine tasks while running locally gives you the sovereignty and privacy that cloud APIs can't match. This is why average 10 tokens per second is acceptable for our use case. We're not having lengthy philosophical discussions about software architecture. We're getting targeted, practical help on specific problems. A model that takes 30 seconds to generate a solid test suite or refactor a messy function is still enormously valuable. With these expectations established, let's define the technical requirements needed to achieve this level of capability. Based on my experience at the time of recording this video, the machine we are aiming for must be able to run an equivalent of the GLM-4.5 Air model at Q8 quantization, with a 64,000 token context window at a minimum speed of 10 tokens per second. These numbers come from my tests with various agentic tools like Klein, Aider, and OpenCode against various models hosted on cloud providers. The experience I had was good enough for day-to-day coding, and I decided to set it as my benchmark. To summarize, 100 to 120 billion parameters, mixture of experts model at Q8 quantization, at least 64,000 token context window, 10 tokens per second of throughput at the slowest point. This is a baseline. For faster, surgical tasks, we can consider a model like Qwen 3 Coder 30B. For architecting and planning, and if resources allow, it would be nice to run larger models like the full GLM-4.5 with 335 billion parameters at a modest speed of 5 tokens per second. On paper, these compute and memory requirements sound feasible. We also should not forget about ergonomic requirements. Since we are building an artificial teammate, it must be quiet and small enough to share our workspace. Ideally, we should be able to put it on a desk without too much damage to the workplace aesthetics. Finally, let's set a reasonable budget for this project. Based on my estimate, and what finally makes it feasible for many, the full setup should not cost more than $10,000 US. It could be less potentially, but let's settle on this amount as it is a fair expense for a professional-grade productivity tool. To run the desired model at target speeds, we need a significant amount of fast memory. At 8-bit quantization, GLM-4.5 Air requires approximately 130 gigabytes of RAM. Here is my estimation. The bulk comes from the model weights themselves, 106 billion parameters at Q8 quantization requiring 106 gigabytes. Add another 12 gigabytes for the KV cache to handle 64,000 token context windows. Then factor in an extra 10%, roughly 12 more gigabytes, for activations, buffers, and other runtime overhead. 130 gigabytes of memory is enormous but achievable. Let's see what options we have and what inference performance they can offer. If we want to achieve maximum inference speed, we should aim for the most performant GPUs we can get. In the consumer segment, Nvidia offers 3 primary options with 24 or more gigabytes of VRAM. The RTX 3090 delivers 35.6 teraflops of compute with 936 gigabytes per second of memory bandwidth, and you can pick one up used for around $900. Step up to the RTX 4090 and you get a massive jump to 92.6 teraflops, with slightly better bandwidth at 1010 gigabytes per second, but expect to pay about $2,500 on the used market. The new RTX 5090 pushes things even further, with an estimated 104.8 teraflops and a significant bandwidth improvement to 1792 gigabytes per second, but you're looking at $3,000 for a brand new card. A great thing about this setup is that it can be configured and optimized for performance needs and budget. We can combine multiple cards to process most of the model on the GPU or offload some processing to the CPU and its RAM. With $10,000 budget, let's consider 3 possible configurations. For simplicity of estimation, they all come with the same AMD Ryzen 9 9950X CPU and 256 gigabytes of DDR5 RAM. The multi-3090 setup gives a total of 96 gigabytes of VRAM at around $8,350. The dual 4090 configuration provides 48 gigabytes of VRAM for about $8,250. And the single 5090 build gets you 32 gigabytes of VRAM for roughly $6,650. The total cost estimation also includes a compatible motherboard, case, robust air cooling, and a high wattage PSU. The configs look sweet. Let's compare their estimated inference performance for our target model, assuming effective offloading. The Quad 3090 setup costs about $348 per token per second. The dual 4090 come in at $263 per token per second, and the single 5090 hits $294 per token per second. Performance-wise, despite higher total combined compute, the 43090 setup falls behind due to communication overhead between 4 GPUs and the CPU. The 24090 shows a marginal advantage in generation speed over a single 5090, but at a higher initial cost. Now let's look at the practical realities of living with these setups. The Quad 3090 configuration is loud at 65 decibels. That's comparable to a vacuum cleaner running constantly. It also pumps out 5,000 BTU per hour of heat, enough to warm a small room, and will add roughly 1,000 kilowatt hours to your monthly electricity bill. The dual 4090 setup is more civilized at 50 decibels. Still noticeable, but closer to normal conversation levels. Heat output drops to 3,000 BTU per hour, and power consumption falls to around 650 kilowatt hours per month. The single 5090 is the clear winner for livability at just 35 decibels, quiet enough for most home offices. It generates only 2,000 BTU per hour of heat and consumes approximately 450 kilowatt hours monthly. If you're planning to work alongside this machine for hours every day, these ergonomic factors matter as much as raw performance. The 43090 produce a massive amount of noise, heat, and energy use, which certainly isn't great to have on a working desk. Ultimately, the single 5090 stands out as a superior choice, delivering the highest peak pre-fill performance while also offering the best ergonomics with minimal noise, heat, and power draw. However, its 32 gigabytes VRAM necessitates significant and slower offloading to system RAM. An alternative to Nvidia cards is Apple's Mac Studio. Two model options potentially satisfy our requirements: M2 Ultra with 192 gigabytes of unified RAM, or M3 Ultra with 256 gigabytes of unified RAM. The M2 Ultra model comes with 192 gigabytes of unified RAM, delivers 27.2 teraflops of compute performance, has 800 gigabytes per second of memory bandwidth, and costs around $6,000 on the used market. The newer M3 Ultra bumps up to 256 gigabytes of unified RAM with slightly improved specs at roughly 28 teraflops and 819 gigabytes per second bandwidth, but you'll pay $7,800 for a new unit. Both models offer slower raw compute and memory bandwidth compared to modern Nvidia chips, but provide a large, accessible memory pool thanks to Apple's unified architecture. This means large models can fit into a single memory space completely, with no need for complex offloading strategies. On the 256 gigabytes M3 Ultra, one could potentially run the full GLM-4.5 model at Q4 quantization and expect a usable inference speed. Let's compare estimated inference performance. M2 Ultra delivers 100 tokens per second for prefill and 20 to 30 tokens per second for generation. The M3 Ultra improves to 115 tokens per second for prefill with 25 to 35 tokens per second generation speed. Clearly, not having to offload processing to slower memory gives a significant and consistent boost during generation, especially with a large context window. Initial prompt processing lags behind the top Nvidia chips due to less raw compute. With cost comparable to a multi-GPU PC build, both Mac Studios offer a compact, nearly silent, and extremely power-efficient design that makes long-term energy costs negligible. This comes at the cost of upgradability and maintainability, as their components are soldered and non-expandable. They also lag behind the Nvidia ecosystem in inference tooling and framework support, potentially limiting access to the latest optimizations and model variants. A 130 gigabytes RAM pool is a high bar, and only a few hardware options can reach it without a high cost. Those willing to sacrifice some performance and output quality for a lower entry cost may consider our bonus option, the AMD Ryzen AI Max Plus 395. Hilariously, this is a real product name that even the most advanced text-to-speech model can't pronounce. This all-in-one system from AMD offers massive unified memory of 128 gigabytes. Memory bandwidth is modest at around 225 gigabytes per second. However, a fully assembled, virtually noiseless, 270-watt TDP computer costs around $2,500, which is only a quarter of our budget. Our target model obviously won't run well on such a machine. 4 TPS is the most we can expect at Q4 quantization. Luckily, one can run smaller models like the Qwen 3 30B A3B at decent speeds. You're looking at 80 tokens per second for prefill and 18 to 28 tokens per second for generation. While this is a significant step down from our target model, it might still cross that good enough threshold for basic coding assistance especially if the model quality is high relative to its size. While it doesn't meet my core needs, some might consider the AMD machine a compelling entry point for experiments, with the perspective of higher quality, smaller open-weight models arriving in the future. Looking at cost efficiency in terms of initial investment per token per second of generation performance, the numbers tell an interesting story. The Quad 3090 setup costs about $348 per token per second. The Dual 4090 come in at $263 per token per second, and the single 5090 hits $294 per token per second. The Mac Studios show significantly better cost efficiency. The M2 Ultra delivers $200 per token per second, while the M3 Ultra costs $222 per token per second. However, this metric only tells part of the story since it doesn't account for the Mac's ability to run larger models due to its unified memory architecture, or the PC configuration's superior absolute performance when models do fit in VRAM. After evaluating all options, the choice ultimately hinges on your specific priorities. For the rawest speed and the flexibility of a customizable, upgradable platform, the Nvidia RTX 5090 PC build is the performance king, albeit with a higher operational footprint. If your priority is a silent, energy-efficient, and hassle-free appliance that just works with large contexts out of the box, the Apple Mac Studio M3 Ultra presents an incredibly compelling and elegant solution. The multi-GPU setups, while powerful on paper, are ultimately hampered by their complexity and poor ergonomics for a home office environment. For those dipping their toes into AI-assisted coding, the budget AMD option proves that capable local AI is becoming increasingly accessible. The dream of a tireless artificial pair programmer is no longer a question of if, but a question of which form it will take on my desk. The parts list is finalized and I'm ready to order. I'll reveal the answer and start the build in the next video, so stay tuned.